So my name is Ryan Sengupta, and I'm going to be presenting my paper and my abstract, Portfolio Optimization Using Volatility Prediction. Okay, so to briefly introduce the paper and the project, interesting one's assets in the stock market is a very significant and weighty endeavor, and a balanced, well-performing portfolio design is crucial to survive any sort of market downturns, managing risks, and to make decent return. So this paper is essentially a dissertation that I've developed to provide some clarity on the easiest way to optimize a stock portfolio. So the approach that we're going to use in this paper, or that we're going to cover in this paper, to construct a optimized portfolio is facilitated through a Monte Carlo simulation. So what is a Monte Carlo simulation? So essentially what we're going to do is we're going to generate the portfolio by assigning random weights to each individual stock in the portfolio and select the the, the combination of the random weights that yields the greatest return. And then with this stock, we're going to forecast the value of the portfolio. With this stock portfolio, I mean, we're going to forecast the value for a certain time horizon. For example, maybe 1 month. And to do this, we're going to use a number of state-of-the-art forecasting techniques that are often used to conduct these forecastings, such as our ARIMA model, the GARS model, support vector regression, gradient boosting, and profit by Facebook, and are going to be compared. And you might ask what entails the processes in some of these techniques. We'll cover that later in the presentation. So moving on to the portfolio optimization, like we said, the Monte Carlo simulation-based mean variance optimization technique is used for the portfolio construction. The weights of the stocks in the portfolio were generated using a well-known probability distribution, the normal distribution, and a weighted portfolio values will be used to calculate daily percentage change. And now that we've done this, a different series is subsequently built out of 10 days of rolling standard deviation and rolling means of the daily percentage change in the portfolio. And by creating this different series, it allows us to achieve stationarity, which will help us with the forecasting using the ARIMA model later on. And after that, we will use the Sharpe ratios for each of the portfolios will be calculated. The Sharpe ratio for each of the portfolios will be calculated for each of the portfolios that were generated using the random weights. And as you can see, we've plotted these various Sharpe ratios from the random weightings on this graph here, and the maximum Sharpe ratio, which is identified with an X right here, is identified and will be used for any subsequent forecasting. So ex ante evaluation. So the goal is so this is basically the forecasting part of it. And the goal is to forecast the value after 1 month. And the following forecasting techniques will be used, like we mentioned: linear regression, ARMA-GARCH, profit by Facebook, SVR. And yeah, so you might not know what some of these are, but I'm going to explain it right now. So linear regression is a linear approach to modeling the relationship between a scalar response and one or more explanatory variables. You can also call these variables dependent and independent variables. So the ARMA-GARCH model, otherwise known as the ARMA model. So yeah, the ARMA-GARCH model has two parts: the ARMA and the GARCH part. The ARMA part, which is the autoregressive moving integrated average model, is a linear combination of the autoregressive model and the moving average model. It's just added together. And the Garch model models the errors of the portfolio produced by the forecast produced from the autoregressive moving average model, the RMM model. And the purpose of this is to capture the observed volatility clustering of the equity returns. So profit. So profit is similar to a generalized additive model in that it has time as the regressor, and it fits several linear and nonlinear functions of time as components. Okay, yeah, so that's profit. And SVR, otherwise known as support vector regression. This approach uses a kernel to map the lower dimensional input data into an n-dimensional space and identifies hyperplanes that capture the best fitting of the observed data. The hyperplane with the maximum number of points represents the regression fitting. Maximum minimum boundaries are also set to eliminate the outliers. Okay, so now we're going to cover the result comparison for forecasting methods. I'm not going to go through each one individually. I'll go over them. You can just take a look at them, each of them. But essentially, the models are compared in 4 different ways. One, in sample accuracy to, for example, how good it fits to historical data. Two, out of sample accuracy, which is how well it can predict the data for a given future time horizon. And 3, the confidence interval of the prediction, whichever one has greater confidence. And 4, each model's ability to manage overfitting. And so I will go through each of the results so you can just take a look. Okay, yeah. So we've compared all of them as of now, and the winner of essentially the winner, the one that gave us the best the best outcome given our criteria was support vector regression. Okay, so now the conclusion. So essentially, a Monte Carlo based approach is adopted to provide transparency and essentially just to save us from the pretty daunting task of correlation prediction in the for the stock portfolio. And continuing with the conclusion, traditional forecasting methods are less prone to overfitting than the non-linear machine learning methods. However, machine learning methods are superior in terms of forecasting error and lighter and tighter confidence interval. And to finish off the conclusion, the traditional forecasting methods tested altogether leads to us coming to the fact that support vector regression outperformed all the other models in terms of both accuracy and confidence. It is worth knowing that the SVR is more susceptible to overfitting, which was one of the criteria that were used to determine which model was the best for the forecasting. So caution should be exercised with in that aspect, but overall, the support vector regression does end up outperforming just because a different model could appropriate for a different choice of risky assets in the portfolio, and any practitioner that would have to go through would have to go through a rigorous model selection process for the portfolio in hand. So future work. There's a few obvious items that are as follows, which of course we couldn't cover in the paper, and just we're developing in the future. So first of all, we didn't cover model selection for the means. The model selection process used for forecasting the volatility should be followed to find the right model for forecasting the rolling mean. Second, methods for selecting the rolling window size. So obviously, so we chose 10 days for our rolling window size, but obviously this is an area of research um, that needs to be conducted because choice of the window size can impact the volatility and its trends. So we chose 10 days, but um, a better prediction could perhaps be could become to um, with a different window size. And lastly, the daily checking of risk parameters and rebalancing when appropriate. So automatic rebalancing of a portfolio is a key component of the portfolio management. A better prediction of volatility can only bring value if the right action is taken at the right time. Automated rebalancing An automated rebalancing process can fill this gap for us. And that's it. So thank you for listening.